This example, as we start off, it's at the top of your sheet. And I'd like you to first identify why this is an interesting and different question, perhaps even more difficult than what we've asked before. Seems very similar to the warm-up that Fatma did, right? In fact, you might even write down a first guess. Yeah? But of course, doesn't that overcount? Do you understand why it overcounts? What's the difficulty here that we're encountering? Yeah. Yeah, we want to recognize that if we have 4 committee members here, before, like in the warm-up, when we were doing it with the one that the part B that Fatma did, if we got, Sebastian, Daisy, Ian, Vivian, that was like a different selection than if we got Vivian, Ian, Sebastian, Daisy or something, right? But now we want to consider those to be the same. So what this counts, 26P4, that would include those 4 groupings as separate things, and for good reason. At one point we wanted those to be treated as separate things and count those separately on our list. We now no longer want those to be separate things. In fact, every single ordering of these 4 people that we select, I want to be counted as only one thing. So did you ever thinking this way about this yesterday? Can you imagine before you all 26P4, big wall of groups of 4, huge list. Can we group those into ones that are really just the same and then divide? Do you remember how I came at one of our repetition problems yesterday in that way? So how many times does this group of 4 appear on our list? How many times? Yeah, doesn't every single arrangement of them appear on the 26P4 list? 24 times, right? 24 times, in fact. So we can be very precise. How can we fix this? By doing what? Divide by 4 factorial. So when we do that, we get our proper answer. Now, to do this, I have taken this and divide by 4 factorial. In general, this seems to be, in fact, it's probably the more useful tool in our tool belt. You'll find that we more often care less about order. So doing this seems to be something we might like to turn into a thing we have like a rule for. In terms of, again, n's and r's, can you give me like a formula now? Can you deconstruct our calculation? If you have n total people or items, and you want to take r of them at a time, disregarding order, what do you have as your formula then? You want to take it? So, go ahead. Yeah, so in general, we have just the NPR formula from yesterday, the n factorial over n minus r factorial, with like another r factorial denominator, right, which takes out the order. We're just dividing out the order, kind of, to fix that overcounting. So, what Sophie said, there it is. I think this is something you've heard before, but again, I want to be able to like man on the street style interview you sometime and not just have you memorize this formula, but I want to be able to like ask you, why does that formula work, right? Like I'd love to have you not just kind of be like, oh, I'm trying, is it n minus r factorial? Which one counts for order and which one doesn't? You should remember where each piece of this came from. Where does the n factorial over n minus r factorial come from? So it comes just from the multiplication principle. And it's just our shorthand way of saying n factorial, but like stop somewhere, right? And then where did the r factorial come from? You should be able to answer just like we did a second ago. Oh, that's us like dividing out the extra amount of order that we didn't, like it's just dividing out the order, the ways of permuting the r items, so that now that it doesn't account for order. So that r factorial takes care of that piece. So I just want to make sure you're clear on that. By the way, your calculator feature is on there. You probably already saw it now that you've looked at that math PRB menu. You saw factorial, you've seen the NPR, and you saw probably on there NCR. Well, that's what this does. It just adds the extra r factorial to the denominator. Obviously, you can do it without it, too. You can just type it in this way, too. Most often, we'll write it instead of the way your calculator has it as this. We'll stack it like this in parentheses, and we'll say out loud, n choose r. Okay. So, the next example comes to us now. Imagine they're unique pencils, and for whatever reason, just imagine that you did something so worthy in this this class, you somehow deserve 3 pencils. Okay, that's a stretch of the imagination, I realize. Okay, I don't think I've ever given away 3 pencils at once to someone. That seems excessive.
Like starting your own pizza place?
Huh?
Like starting your own pizza place?
Oh, there's a, yeah, you got the pizza. The pizza. One way. Gotta do the pizza. So what are you going to do? I mean, this is hopefully a straightforward application of the previous problem. So when you're ready, just give me the answer, Leo. I know I'm ready. What's the calculation you're doing on your calculator? Yeah. Yes. You got it? Yeah, so what's the calculation you're doing? Yeah, 20 factorial over 3 factorial, 17 factorial, which is just 20. Choose 3 is what he's saying, and that comes out to, he says, you can just do 20 and then NCR and then 3 on your calculator too, or you can do the factorials, whatever. You try both just to make sure they both work.
Okay, wait.
I don't know where it would be back there, so you can look around. But it also should be right on the top and everything over there in the far corner. You see the extra algebra 2 materials? What'd you get there? 1140. People agree? Yes? Okay, moving along to the next problem.
Thank you.
Yeah, you're welcome. Alexis, when you're ready, tell us the answer to that one. Both the calculation you're doing and the number you get. You have that one yet? No, not yet. Okay, not mentally a trick question yet. We do have some trick questions, but not yet. This is good. By the way, this is a perfect example. Cards are a great example where combinations is what we care about, right? No one cares about what order, usually. The cards are dealt into you. You get a hand of cards and you got like an ace, a king, and a 3. That's the same as if you got a 3, an ace, and a king. That doesn't matter.
To be completely honest, I'd be more likely to start like a casino as something that in the first place, since it's only the fact that I know basic probability.
Yeah, house always wins.
That's basic probability.
Make a bunch of unfair games.
The best part is you can make the slots so that you will almost always win.
All right, Alexis, go ahead. What's the calculation and what is the answer? Thank you, guys. 52 what? Choose 4, yeah. 52 choose 4 is equal to something large. Agree, people out there? Got a lot of 4-card hands, yes. All right, then next do these two together here. Turn to your neighbor, tell them how are you going to calculate 5 and 6? Tell them how you're going to do that. Tell them. If you're having trouble with any of these at any point, actually picture yourself taking out a deck of cards and physically creating every 4-card hand that's made of spades. Like what would you do? What would you actually physically do to start doing that? Let's do it. Make every 4-card spade hand. Go.
Okay.
But then I think it multiplies by
Like just divide the last one by 4. Divide by 13. It's out of the entire deck. No. Not just out of the 13. You wouldn't do 52 with it. I can't do right either. So 4 factorial. I already thought of that, and that's down. You're right, we get 20 up and you got 25. Yeah, dividing that by 4 is not giving you any number. The whole division thing wouldn't work. She said maybe if we divide the previous number by 13, but that wouldn't work because by that same logic you divide it into 4 for just spades as opposed to all suits.
Do you want to think how would you actually start to reduce your deck to
But I thought it was out of all cards, so it's
No, it says how would you actually begin to do this? Would you take throw away all the cards and start making more cards? Isn't that how you do it?
which means the next question is just that time 4.
All right. Let's come back together on these 2 questions. Vivian, talk us through both of them, if you will. Go ahead. You got it? Franklin's listening really carefully. Watch, you'll see. Wait till you hear what Vivian has to say. It's amazing. Go ahead. This is 13, choose 4, because, again, if you're ever having trouble with these, just think about what you would actually do, right? What did that come out to? 715? So if you're ever having trouble with these, what would you actually do if I gave you a deck and said start making all the 4 card spade hands? Wouldn't you start by throwing away every non-spade? Be like, okay, did you mean
No, I'd start by dealing them to people and
okay,
grading them all.
Ian, that's the last comment, sorry. Okay. They've been great comments, but we're done now. Yeah. We're choosing 4 from among 13. Right? So reducing our deck to a 13 card spade deck, and then we're from those choosing 4 without restriction. Okay? And then, yeah, what's going on there? Explain yourself. Does that follow? She says there are 4 suits. So any one of them, a 4 card club hand, there's 715 of those. So add that up. 715 for the spade, plus 715 for the hearts, plus 715 for the diamonds, plus 715 for the clubs. That's a total of whatever 4 times 715 is.
2,860.
Okay? You can also picture that as a tree, a decision tree, right? If you're not sure why multiplication is the correct move to make there, think my first decision in life is to pick a suit. Well, let's see, how am I feeling? How about diamonds, right? You have 4 options for that. And then underneath each one of those suits on your tree, get ready, you have 715 branches underneath from 13 cards that are diamonds, say. You have 715 4-card hands you can make from that, can't you? So you have a tree that goes 4, and then 715, right? And every root through that tree represents one of our 4-card hands that's of 1 suit, right? And that tree is easy to count. You just do 4 times 715. Can you picture it? I'd rather not draw it, right? Okay. All right. Sorry, we're stretching you here. These get a little tricky. I encourage you to think very carefully about the first question first. Exactly 2 threes, and then let's worry about the at least 2 threes in it. Let's first of all focus really hard on the first question. At least exactly 2 threes. How do we do that? Again, I encourage you to think about actually picking up a physical deck. What would you do first? You took all the cards. And you actually started trying to build 5-card hands with 2 threes and 3 non-threes. Why would you ask? You should take one and raise it to the other. divide it into two piles, threes and non-threes. And from each pile, you have some decisions to make, wouldn't you? How many ways are there to choose from 4 threes? 2 of them. How many ways are there to do that? I don't know, but it's 4 choose 2, right? Yeah? So that's what I'm doing in one pile. That's the number of ways if I have 4 threes to pick 2 of them. How many ways are there to pick the other cards? What counts that? What counts that? 48 choose 3, right? There are 48 non-threes. We're required to have 3 of those. And then I had a friend who asked me, should I put like a plus sign here? A minus? A times? Should we exponentiate? What should we do? And why? What are you going to do? Those both do count individual things that are important to us, I think, right? The number of ways of selecting 3 cards, and the number of ways of selecting 2 cards, 2 threes, right? Those are important to me. Rin says multiply. Are you just guessing? No, you have reasons? Yes. Share them. I'm not ready to put a times there to explain why you think it belongs there.
Because like any of them can be paired up with any of the other.
Yeah. Could you make a tree for this?
Yes.
How many ways are there to do this? What does this come out to be?
6.
6. So in our tree we have like 6 branches at the top. That'd be 6 ways to select the 3. And on each of those branches, if you love trees, you'd have 48 choose 3 new options for how to select the other 3 cards. So I think multiplication is what we want. The key word is for each, right? For each selection of 2 cards, 2 3. Like in fact, isn't that if I actually literally asked you to do this, let's go further. Not only would you start by separating the piles of 3s and non-3s, what would you do? I think what I would do is I would select 2 3s and then make every selection of 3 cards that I could to go with them, wouldn't I? And then what would I do again? Now I'd repeat with 2 new 3s. Right? So do you see it? Do you feel the multiplication? For every selection of 2 3s, there are 6 ways to do that. Right? There are 48 choose 3 ways that we need to account for each one of those. Right? For each being the key word that implies multiply, or can you picture a tree? Whatever. Anyway, so that's the calculation that gives us the first answer. The second one is even more complicated. And I know some of you are very tempted, because I saw as I walked around, almost everyone did this. I don't know if anyone would have said this directly. Here's the way I need you to approach this, okay? Be very, very careful with this. This is a really terrible calculation, okay? Do you agree that you would know how to calculate this for 2? Oh yes, I've already done that. What if I asked you for 3? Exactly 3 threes. What about exactly 4 threes? Could you make all those calculations? Yeah, that's what we need to do.
Is that what you, and then
So the thing we already computed, plus the number of ways of getting 3, 3 threes and 2 non-threes, right? Wouldn't that be? I think we're okay. All right, so this is, and then we're done there. We can't do 4 choose 5 and 48 choose 0. We can't get 4. You can't get 5 threes, right? So we're done there. Those are. This is the number of ways of getting. This is the total number of ways we already established of getting two threes, exactly 2 threes and 3 non-threes. This is the number of ways of getting exactly 3 threes and 2 non-threes, and this is the number of ways of getting exactly 4 threes and 1 non-3. So figure that out. That's like complicated. By the way, what is 4 choose 4? How many ways are there to choose 4 from among 4? Yeah, 4 choose 4 comes out to 1. What's 48 choose 1? Is that another obvious one too? How many ways are there to choose 1 from among 48 things? That comes out to 48, okay? So I'll write them this way just for the sake of symmetry. But really those you don't need a calculator for. Yeah, Annabelle has an objection, I can tell.
Now, is there a better way to
No.
do this because of
No. I know some of you are tempted, I've taught this long enough. Some of you are tempted to say 4 choose 2 times, well, I don't know, 50, because that's what 50 choose 3, right? Like, let's just have that remaining pile. But keep in mind that, now, let's see if I can explain this without using the word independence. You can't have, what you need to have in order to do this is 2 separate piles, and nary the 2 shall meet, right? So once you've separated them, you can't like meddle with them afterward, right? So 4 choose 2 counts the number of ways of selecting 2 from among 4 threes. But then, which 50 cards are you talking about if you put a 50 here? Are they ones, you've like mixed the piles now as you went from here to here, right? Does that make sense? So they're not.
If you have like a really big pile and let's say like at least 2 things you had to do, you know, like 5 or 6.
Yeah. It would be a terrible calculation. You'd want a computer to help you. Yep. Exactly. And we will address that question even in this unit, the one you just raised. Yeah. All right, great. So feel free if you object to this to calculate your own way and see that it doesn't come out correctly. Okay. But this is right, and it is a mess, but it is the only right way to do it for us. Okay. Next question is not meant to be hard. That was the hardest question on here, I think, right there. That one right there. They don't get any harder today. Okay, keep going. Today. So I'm ready to hear from someone here. Not a trick question on this, but when she's ready, Maki's going to give us the answer to the men and women thing here. Maybe she has it now. Do you have it ready already? No. Okay. I should really reorder these questions on the handout, shouldn't I? The one we just did is much harder. You ready? She's got it. Don't say it like that. I remember, you at least have the calculation. What are we supposed to do at least? Wait, listen. Yeah, and whatever that equals, I don't know. Do you have it? 150? Why don't you add them? I don't know, we should talk about this again, right? So, for every, this is the key word, for every 2 you choose from among the men, don't you have to form all 5 choose 2 committees of women of 2 to pair with those 2 men? All right, now pick 2 new men, do it again, all the same again, you're multiplying, right? I like this one, right? We got pizza here. It's an interesting question. Let's start by making the assumption, by the way, that like if you get pepperoni and mushroom pizza, that's the same as getting a mushroom pepperoni pizza, right? Would you reject the order? Like if the pepperoni came out on top or the mushroom came out on top, you'd be like, excuse me, I ordered a pepperoni mushroom pizza. Right? We don't care about, right? Like, that's not part of the deal here, right? The order doesn't matter. So let's start with a simpler question than this, because this whole offering of optional toppings is interesting to me, right? Let's assume you want 3 toppings. How many ways are there if there are 9 available toppings? How many ways are there to?
Wait, but it doesn't say 3 of them.
No. I'm just saying. Like, let's say you want 3 toppings. How many ways are there to choose to create a 3-topping pizza?
We use toppings multiple times with
Yes.
cheese.
No. You can't have like 2 helpings of pineapple. That's not part of this. We can change the problem to make that happen though. Right? I have a way in on that, but that isn't the problem as written. No one has answered my challenge yet. What if I only want? I know we want a 3-topping pizza. How many 3-topping pizzas exist at this? 9 choose 3. You got it right. But of course, how many ways are there to choose to create a 5-topping pizza? Yeah, and this time I think adding is the right word, Cassie. Right? All the way from what? 9 choose. Do you have to have 1 topping?
Yes.
No.
What?
I don't know, you can change the rules if you like, but.
When you're adding them,
Why are we adding them? I don't know. I just heard what Cassie said. That's this here. Yeah, what is 9 choose 0? That's how many ways are there to have no topping? What is 9 choose 0? Yeah, there is one no topping pizza, right? Doing that calculation, by the way, 9 choose 0, involves you doing 9 factorial over 0 factorial 9 factorial. What is 0 factorial? Do we know? It is 1, and if you didn't know, now you know. Okay, so moving on down the line, we get 9 choose 8, and finally 9 choose 9. What's 9 choose 9 also? 1 also, right? 9 choose 9. How many ways are there to have 9 toppings? It's easy. You just say, I'd like them all, right? One way to order that, okay? Good. Some of you are busily hammering buttons. But while you're hammering buttons, let me give you a new fresh of breath air on this problem. Breath air. Let me give you some breath air. All right, here's a refreshing way to look at the problem. Are you ready? Allow me to interview you, okay? So you're here ordering a pizza, I understand? I'm going to go down the list. Would you like mushrooms? Yes or no? Pineapple? Pepperoni? Anchovies? Gummy bears? Oh, you didn't see that one coming, but you said no. Okay. What else do you like on pizza?
Salt.
Extra cheese.
salt? Did you say salt?
Salt.
No. All right.
Both of those are weird.
What am I asking her? How many questions am I asking her?
So many.
9. And how many answers are there to each one? What do you think another way to count this is?
2 to the 9.
Those who are hammering this in, did you finish?
Oh yeah, I knew
Okay.
I saw that number somewhere before.
Yeah, so I mean this is a little bit of a crazy mystery that this would add up to this. Let's just save that up in our hearts and figure out like later why that might be true. But it is a quicker way to calculate this. Notice how counting problems can sometimes be hard, or maybe they're easy depending on what light we bring to them, right? Yeah.
Okay, so I know this one seems a little similar to the one that was like the 4 choose 2, like the really popular one. So why is there an easier way that you missed or not?
Well, we do have more discussion to have on the last problem a little bit, right? Some of the stat people in the room may even recognize the tools we might need for counting some of that. Yeah. Oh, yes or no, right? So there are 2 options to each question. 2, yes or no, yes or no, yes or no. So you can build a tree, yeah, right? Or you can build a tree with 512 branches. 2, it's a binary tree. At every turn you have 2 options, right? And you would have a route through the tree. Her route through the tree was yes, no, I think no, no, yes, yes, right, whatever. And every time we get to the bottom, we have a route of yeses and nos to trace what pizza we have. All right, so 3 required you must have a sandwich. So we have 3 options for that. You must have a side. 4 sides.
You must have.
You
Wait, why is this for multiplication?
must have a drink. Again, can you build a tree here, right? So for each sandwich, for each one of 3 sandwiches you might choose, you have 4 sides that could go with it. And for each one of those 12, 3 sandwich side combinations, right? You have 5 different drinks that could go with them, right? For each of those, right? So do you see why multiplication? I want to have you make sure you hear this. But then this is interesting. 5 optional toppings. What do I do then?
Is that like the pizza thing?
Well, that's like what we just did, right? That means really you have like 5 more things to say yes or no to, right? So you could just say times 2 times 2 times 2 times 2, right? Times 2, whatever. 5. Tons of time. Ready, go. Wait, we don't. We only have this one, right? Yeah. Oh, we get tons of time. Okay. Normally we can skip the last example. All right. How do we ensure that B must be included? We're choosing. Nice. Huh? We have 7 people, A, B, C, D, E, F, G. If it's without restriction, what is it? If there are no restrictions, what is it? It's just 7 choose 3. What if B must be included, though?
6 choose 2.
Yeah, now we've forced our hand. There are only 6 people we have to choose from and 2 slots to fill.
Remember that we have 6 choose 3.
What about if D must be excluded? Yeah, now we only have 6 people to choose from, but we still have 3 slots to fill. Not these, in the end, these are not hard. The arithmetic is not
5
hard.
choose 2 plus 5
Huh?
choose 2.
Well, aren't there 6 people for 2? Aren't there 6 people to choose from now?
Yeah, no, I'm just gonna.
Oh, this guy here?
Third one there is 5 choose
Oh, yeah, I don't know.
5
Let's
choose
see. How do we do
plus
that?
6, 5 choose 30.
C and E cannot both be on the committee because they don't get along. We'll leave that one a mystery.
2 times 5 choose 2.
You gotta have mystery left in your life. Homework 2 tonight, you'll be great. See you on the morrow.